Hi everyone, welcome to the fourth weekly live session of this NPTEL course of Remote Sensing Principles and Applications. Uh, this is brought to you by NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme from the Interdisciplinary Center for Water Research (ICWR) at IISc Bangalore. And this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. So, just a brief information about this course contents and everything. The video recordings of the session will be made available on the YouTube channel. I've already shared the video recordings of the first three weekly live sessions. The files relevant to the sessions will be made available through a Google Drive folder. The files and the video recordings will be made immediately available after the class. And the images, if taken from the internet, are solely for study purpose. We don't intend to plagiarize or any copyrighted content. So these are the first three weekly live sessions which I've already uploaded on the YouTube channel. And this the link underneath is basically the spreadsheet link which contains the YouTube links for the videos as well as the Google Drive folder which contains the illustrations from these live sessions. So today we would be basically solving a set of questions, and through those questions we would get to learn about some of the remote sensing techniques. We would be yeah, I'm recording it. We would also be checking whether from the next weekly live session onwards. Oops, someone is trying to enter. So we would be solving a few questions today to understand understand the radiometric resolution concept better. So let's see, and I also plan to illustrate a few coding examples of remote sensing. But I also thought that the week 6 contents would be uploaded by the NPTEL community by the time I start my next weekly live session, which unfortunately has not happened. So, in the next weekly live session, apart from the questions to be solved, we would also look at some coding examples. This we could not do this time because the contents were not actually uploaded by the NPTEL team. Anyways, so the first question discussed today is how many color values are possible in a three color, three band Landsat 7 image. So one thing which you need to recall is that the radiometric resolution of Landsat 7 is 8-bit. So this would mean that there are 2 to the power 8 discretizations, which is equal to 16 times 16, that is 256 discretization. So anyways, just a brief about what we gave in the last class. So there will be 256 grayscales. The one at the bottom, or the one with DN number 0, and at the top it would be something known as the DN number 255. So when we move from 0 to 255, the total discretizations will be 256. So the bottommost DN, the DN with the lowest value would be the purely black pixel, and DN number 255 would be purely white. And the ones in between would be different grayscales. Uh, um, Transitioning from darker grayscales to brighter grayscales as we transition from DN equal to 0 to DN equal to 255. Anyways, so this question asks you to find a possible range of possible number of color values in a three color, three band Landsat 7 image. So there are three bands as already illustrated by this question. So what might be the number of different number of colors possible would be 2 to the power 8, and this would extend for the colors as well as the band. So the actual answer would be 256 times 256 times 256, which is 256 cubed, which is actually 16777,216, which is actually greater than 16 million different color values. So that is what this question asks for. Anyway, so this was the case for Landsat 7. Let us just wonder what would happen with Landsat 8. I would take another slide to illustrate that. For Landsat 8, we know that the radiometric resolution is finer for a Landsat 8 than the Landsat 7 interface. So that is actually 12 bits. So the total color values in that case would be 2 to the power 12 times 2 to the power 12 times 2 to the power 12, which is in fact greater than 68719 million. So you can see how with an increase in the radiometric resolution, the color values increase. So for Landsat 7, versus Landsat 8. Landsat 7 was an 8-bit radiometric resolution. Landsat 8 is 12-bit. Color values were, I think, in excess of 16 million. And for Landsat 8 would be in excess of 68,719 million. So it's actually a massive increase as you increase the radiometric resolution from 8-bit to 12-bit. So let's see the next question. Following is an example of data format in which a 3-band image data of size 3 by 3, that is 3 rows and 3 columns, are stored in the BIL format. How would the image look like after you have converted it into an image? So these are the data files given. So 3 by 3, so 3 by 3, okay, and there are 3 bands also. So total number of data available should be 3 times 3 times 3, which is equal to 27. So we do have 27 different types of data values here, and we want to use the BIL format, which is the band interleaved by line. So let's try it out. BIL is basically, you have already studied it in the earlier weeks. Okay, so we want to store it in a 3-band image of size 3 by 3 each. So let us suppose this is the first band of size 3 by 3. Band 1. This is the second band. Band 2, and this would be the third band, let us say, again of 3 by 3 size. So in each band you can store 9 different pixel values. So this is band number 3, let us say. Okay, so we are doing band interleaved by line. So what would we do here is that firstly we would be filling up each line of each band. Let us say we would be filling up the first line of band number 1, then we would be filling up the first line of the band number 2, then we would be filling up the first line of band number 3, then we will straight away move to the second line of band number 1, second line of band number 2, second line of band number 3, then the third line of band number 1, third line of band number 2, and third line of band number 3. So this is how it would happen. So 45, 12, 21 would be in L1, line 1 is L1, okay, L1 and band 1, okay. So these would go to line 1 but band 2, so B2. This is how I'm showing it. Okay, then again 3 values. Let this go to L1 but B3. Then these 3 would go to L2 but of B1. These 3 would go to L2 but of B2. These 3 will again go to L2 but of band number 3. These will go to L3 of band number 1. This again will go to L3 of band number 2, and the final 3 data values will go to line 3 of band number 3. So this is how we will do it. So let's just fill it up. It's very simple now. So 45 will go here. So this is line 1, this is line 2, this is line 3, L1, L2, L3, L1, L2, L3. It's very straightforward. 45, 12, 21, 47, 100, 25, 2, 0, 19, 34, 65, 76, 78, 87, 66, 12, 65, 98, 24, 22, 52, 15, 69, 66, 85, 66, 99. So it's very straightforward. I mean, the BIL storage format, right? So I think it's clear. Let's solve the same question, but in the question number 3 would be storing it in the BIP format. BIP format is band interleaved by pixel, basically. We know that there are 3 common data storage types: BIL, BIP, and BSQ. BSQ is band sequential. So I intended to take examples which would illustrate all the 3 types to you. So the second one is BIP. So this is band interleaved by pixel. So let's again make those 3 bands. This is band number 1. Let this be band number 2, and this would be band number 3. Band 1, band 2, and let this be band number 3. So we are basically filling up each pixel location first. Okay. So let me show how it actually works. So this 45 would go into the first pixel location. Let me just show the pixel locations. Let this be pixel location 1, pixel location 2, P3, P4.
Excuse me, sir.
Yes, please.
Can you explain, please, again?
Which part? BIL or BIP?
Both.
Okay, sure. So in band interleaved by line, what do we do is that we fill the data. The data is already given in the data file. Okay, so we are filling it line by line of each band. So this is line number 1. The first top row is the line number 1. The next row is line number 2, and the third row, which is basically the last row, is the line number 3. Okay, so there are first 3 values: 45, 12, 21. They would be the line number 1. They would be stored in the line number 1 of band number 1. Then the next three values, 47, 100 and 25, would be stored in line number 1 but of band number 2. So we have stored it like this: 47, 100, 25. Then another set of three values, I mean right after that, 0, 2, 0, 0 and 19, they would be stored in line number 1 but of band number 3. So on, I mean this is how we go. So the first three set of values would be going to L1 B1, then the next three set will be going to L1 B2, then the next three set will go to L1 B3, then after that the three sets will be three set of values will be going into L2 B1, then L2 B2, L2 B3, L3 B1, L3 B2, L3 B3. Is it clear to you?
Yes, sir.
Okay. So let's move to the band interleaved by pixel example in that case. So I mean, I've kept the data values as same. I mean, just so that you can understand that there is a particular difference between them. Okay, so now this is band interleaved by pixel. So let us suppose I am making a 3 by 3 image matrix which is on the top right. Okay, so the pixel locations would be P1 means pixel location number 1, P2, P3, P4, P5, P6, then comes P7, P8 and P9. So these are the pixel locations. So we would be filling up the pixel location number 1 of each band first, then pixel location number 2 of each band, then pixel number 3 of each band, pixel number 4, pixel number 5, pixel number 6 till pixel number 9. So that is the story of this. Clear, right?
Yes, sir.
Okay, thanks. So let us just fill it. So 45 would be put into pixel location 1 of band 1. 12 would be put into pixel location number 1 but of band 2. 21 would go to pixel location number 1 of band 3. 47 will go to pixel location 47 will go to P2 but of band 1. Then 100 would go to pixel location number 2 of band 2. 25 will go to pixel location 2 of band 3. 02 will go to pixel location number 3 of band 1, and so on and so forth. This is how we will move. So 99 finally will move into pixel location number 9 of band 3. 66 will be in the pixel location number 9 of band 2. 85 would be in the pixel location number 9 of band 1. So this is how we will fill it. So let's do it now. So 45 we will fill here, then straight after that 12, then 21 in the band number 3, then 47 will be filled here, 47, then 100, then 25, then 02, 00, 19, 34, 65, 76, 78, 87, 66. So till that I have done. Then 12, 65, 98. This is also done. Then 24, 22, 52. This also done. 15, 69, 66. So this is also done. And final three are 85, 66 and 99. This is how we store the data for the BIP format, which is the band interleaved by pixel. The last question in this series is band sequential. I mean, the third format of storing data. So what do we do is that we fill up each band first, the complete band first, then we move into the next band, and so on and so forth. Okay, so this is the same question, but I would illustrate it. No need to worry about it.
सर जो ये सर जो ये डेटा फाइल है सर, ये सर कैसे मालूम पड़ती है?
आई एम नॉट अंडरस्टैंडिंग डेटा क्या मालूम पड़ता है, क्या पूछ रहे हो तुम?
जो सर क्वेश्चन दिया हुआ है इसमें फॉर्मेट बीएसक्यू वाला फॉर्मेट हो गया, और जो डेटा फाइल दिया हुआ है
हाँ,
ये हमको कहाँ से मालूम पड़ता है इसमें फिल करने के लिए?
ये तुम्हें करना नहीं है, लेकिन अलग अलग जो सैटेलाइट सेंसर होते हैं उनके अलग अलग फॉर्मेट्स रहते हैं, ठीक है ना? तो ये हमें करना नहीं है, लेकिन ये मैं इलस्ट्रेट कर रहा हूँ कि कैसे होता है स्टोरेज।
अच्छा।
This may be, I mean, more interesting to you in case you are actually storing some data from a site. You may be going to several locations, carrying a GPS sensor with you. You will be finding some, let us say, soil moisture values from several locations from a plot. Okay. Then how would you rasterize that data? This is a method to rasterize the data, by the way. So there are several ways to rasterize the data. So one of the bands may be, let us say, the soil moisture. One of the bands may be soil temperature. One of the bands may be, let us say, the cation exchange capacity. Okay, so the government nowadays is trying to benefit the farming society by making some soil health cards. So if you, let us say, extract the data from them and you try to rasterize it, you would need to require these techniques. You understand, Saket?
Yes sir.
Oh, okay, thanks. Let me move on to the third question in that case. If you want to ask anything else, please feel free to unmute yourself and shoot your question straight away. No issue with that. Okay, so we are again doing the same thing. This is, let us say, band 1, this is band 2, and this is band 3. These are the data. So the first 9 data, 45, 12, 21, first 3, next 3. Okay, so all these 9 data will go to band 1 straight away. This will go to L1, the line 1 of band 1, then line 2 of band 1, then line 3 of band 1. Then again the first 3, I'm grouping them into 3. These will go to band 2, L1, L2, L3. Again I'm grouping them in 3. These would be band going into band 3. So this is L1, this is L2, this is L3. So this is how we will be storing it. So let me show that. So this is line 1, line 2 and line 3. So this is 45, 12, 21, then 47, 100, 25, 02, 00, 19, then straight away to the next band, 34, 65, 76, 78, 87, 66, 12, 65, 98, then 24, 22, 52, 15, 69, 66, 85, 66, 99. So this is how we fill it for BSQ, which is band sequential. So we saw the 3 classic ways of storing data. The first one is band interleaved by line. So just like the name suggests, there is L in this word. So L stands for line. So we are filling up each line of each band first, and that is how we succeed in this. The next one is band interleaved by pixel. So we are filling up each pixel location first of each band. Then we are moving into the next pixel location of those bands, and so on and so forth. And the third one is band sequential. I mean, it's the name itself suggests that it's filling up each band sequentially. So we are filling up each band first of all, then moving into the. We are filling up the first band completely. Then we are moving into the second, third, fourth, and so on and so forth. So this is the way to, I mean, store the data. So I used all the three basic examples to understand, I mean, make you understand this strategy. Now, the next question, the question number 5, is about conversion of DN value to the top of the atmosphere spectral radiance. Okay, so in uh, in level 1 data of Landsat, let us say Landsat is a classic satellite, first of all, which has data for more than 50 years. So even if you want to check the land cover of your, let us say, village of 1980s, you can freely download the data from the USGS Earth Explorer website and see how the landscape was there in your village. Okay, so that is what this Landsat series enables us researchers to do. Anyways, so the question is about conversion of a DN value to digital number value to the top of the atmosphere spectral reflectance. So we are trying to convert digital numbers to top of atmosphere radiance, not reflectance, radiance. Okay, so the data given by Landsat sensors is actually a level 1 product is actually the digital number itself. Let me just write what these levels actually mean. So Landsat level 1 is actually quantized, and quantized means DN values. There are I mean, for 8 bits there would be 2 to the power 8 quantizations, means from 0 to 255. For 12 bits, there would be 2 to the power 12 quantizations from 0 to 2 to the power 12 minus 1, and so on and so forth. Quantized and calibrated scaled digital numbers, and Landsat level 2, those are actually atmospheric corrected data. Corrected data which would represent in general the surface reflectance. Okay, so let's see it in the next slide. The Landsat level 1 data can be converted into top of the atmosphere spectral radiance using the radiance rescaling factor. So radiance L lambda would be ml qcal. Qcal is nothing but a dn plus an additive unit. So ml is the multiplicative coefficient, al is the additive coefficient to this. So L lambda is would be the top of the atmosphere spectral radiance, in units of watts per meter square per steradian per micrometer. ml is the band specific multiplicative scaling. Factor which is available from the metadata. So this metadata along with the actual data of the image, you can even download the metadata from the USGS Earth Explorer website. We would be showing it in the next weekly live session. So this for Landsat. is available in the USGS Earth Explorer website. You can also download the data on your own, by the way. So it is free to download. You just need to make an account, and you can download data even from 1970s, 1980s, 1990s, even till a few days back. It is almost real time. Okay, so this is represented as, yes. Is there any question? Someone unmuted.
No, sir.
Okay. Radiance band x, where x is the number of the band. X is band number, by the way. And there are several bands in the Landsat program, by the way. So these are the bands for Landsat 8. Okay. What else? So we also want to know the what is AL. AL is the band specific additive rescaling factor from the metadata again, and this is represented as radiance, sorry, add band x, where x is again the band number. Okay, and finally I would take another slide to explain this. QCal is nothing but the quantized DN numbers. I mean DN numbers basically, nothing else. Quantized and calibrated. I mean whatever the level 1 product gives. So that is QCal. Standard product pixel values. Nothing but the DNs. So L lambda was equal to ML QCal plus AL. Also another thing which we understood was that ML and QL, ML and AL, which are the coefficients, they would actually depend on the band numbers. So they would vary with respect to the bands. So the question actually wants you to convert the DN value of 45 to the top of the atmosphere spectral radiance. So this would be 45, L lambda equal to ML times 45 plus AL. So where to get the ML from? So ML and AL from? ML and AL are already provided. As you can see, this is ML and this is AL. They are already available in the metadata of the image, by the way. So, and you can clearly see that with the changes in the bands. So this is the Landsat 8. These are the Landsat 8 bands. There are 11 of them. With the changes in the band numbers, the multiplicative rescaling factor as well as the additive rescaling factors are actually changing. So we are interested in what? We are interested in band number 10. So the ML for band number 10, we can extract it. It's already highlighted. It's 3.342 into 10 power minus 4, and AL for band 10 is actually 0.1. Just substitute it in the previous one. 3.342 into 10 power minus 4 times the DN, which is 45, plus 0.1, which was the additive rescaling factor. So L lambda would come out to be 0.115039 watts per meter square per steradian per micrometers. So this is the thing. Okay, so how do we solve L lambda for, let us say, band 1? It would be taking the coefficient for it, 1.2587 into 10 to the power minus 2 times the dn, which is available in band number 1, by the way, minus 62.93359. So this is the one for band 1. What would be the top of the atmosphere radiance, spectral radiance for band 2? 1.2889 into 10 to the power minus 2 times dn given in the band 2 minus 64.44476 and so on and so forth. So this is how you can do L lambda, or the top of the atmosphere spectral radiance for band 11 would be 3.3420 into 10 to the power minus 4 times dn, which is given in band number 11, plus 0.1. So this is how you basically find it out, I mean, for each of the bands. This is a very simple process. These values of multiplicative rescaling factors and the additive rescaling factors would be already available to you as a metadata, so no need to worry about that too. So this was the first method of finding the top of the atmosphere spectral radiance. There is another such method, by the way. So let's check it out. So method 1, it is also known as the gain and bias method. So it uses gain and bias. Bias is also known as the offset values. And method 2 uses Lmin and Lmax. I will explain what these Lmin and Lmax are. Spectral radiance scaling factors. So let's see the method number 1, M1, is nothing but the gain and bias method. So we already discussed about it, but let me just write the expression again. So it is gain times dn plus bias. So gain is nothing but the multiplicative rescaling factor, and bias is nothing but the additive rescaling factor. They're the same things. So L lambda is the radiance of the cell, and dn is the digital number of the cell, and gain and bias depends on the band. You know it very well. I already explained it in the previous example. So this would be multiplicative factor is nothing but the gain, and this is nothing but the bias. This takes a very well-known expression. It's very similar to a well-known expression, that is y equal to mx plus c, where m is the slope and c is the intercept. So for a 8-bit system, let this be L lambda, let this be dn. 8-bit system, it can move from 0 to 255 only. Okay. So this part would be the intercept, which is the bias, and the slope would be the gain. It's just a linear expression, nothing special as such. Okay, so this was the method number 1. Let's check out the method number 2. Method number 2, the top of the atmosphere spectral radiance is found out like this. L max lambda minus L min lambda by Q cal max minus Q cal min times Q cal minus Q cal min plus L min lambda. So it's very similar to an interpolation technique, by the way. So let me write the meanings. L lambda is basically cell value as radiance, the spectral radiance. Q cal is nothing but the digital number. L min lambda would be the spectral radiance scaled to Q cal min. L max lambda is the spectral radiance scale to Q cal max. Q cal min is the minimum quantized calibrated pixel value, which is typically equal to 1. Q cal max is the maximum quantized calibrated pixel value, typically 255 for 8-bit image. Okay, because there are 256 discretizations and so on and so forth. So the radiance will finally be like this. Radiance is equal to L max minus L min by the total number of difference in the discretizations, that is 255 for an 8-bit system, into the digital number plus L min. So it is nothing but an interpolation technique, by the way. The values between the max and min are already available, so in between you are just interpolating. So let's take an example. Let us assume a hypothetical 10-bit sensor. So this implies the number of discretizations would be 2 to the power 10, which is equal to 1024. So let's say we are finding the the radiance corresponding to digital number 400. Say digital number is 400. So digital numbers can vary from 0 to 1023 in a 10-bit setup. So in that case, the radiance would be L max minus L min by 1023 times the dn given plus L min. Again, assume some values. Let us say L max is 600, L min is 0.63. So just plugging them into the equation above, the radiance will come out to be equal to 600 minus 0.63 by 1023 times the dn, which is 400, plus the L min again, which is 0.63, which comes out to be, or I shall write it in the next slide itself. It's getting too cramped like this. Okay, so the radians, just putting the values, would come out to be 600 minus 0.63 by 1023 times 400 plus 0.63, which is actually 234.98. That's it. So this was a step through which you can convert the dN into the spectral radiance, the top of the atmosphere's spectral radiance. So how would you find out the top of the atmosphere spectral reflectance? Let's find it out. There is another step to it. Converting to radiance to top of the atmosphere reflectance. So the reflectance, planetary reflectance rho p is pi L lambda d square by E sun lambda times cos theta s. So the top, the numerator, the top part, the numerator is nothing but the radiance, and the denominator is nothing but the irradiance. So the ratio of the radiance to irradiance by definition is the reflectance. So radiance is the radiance leaving the earth and irradiance is the radiance reaching the earth from the sun. So this ratio will always be less than 1. In general, rho p is in between 0 and 1. So this rho p is something known as the planetary reflectance. It is unitless because it is the ratio of two different radiance units itself. So rho p would vary from 0 to 1. It would be low for, it would be, I already showed you the spectral reflectance features of the three very common surface features, namely water, vegetation, and soil. Bare dry soil, healthy green vegetation, and clear water. And we also discussed that the reflectance of water in the near infrared zone would be tending to 0. It's almost 0 basically. Whereas the reflectance of vegetation is very high in the near infrared region. It's almost around 50% or 0.5 in this unit. And bare dry soil consistently shows relatively larger values of reflectance. L lambda in this case would be the, someone trying to enter. L lambda is a spectral radiance at the sensor's aperture and we calculated it in the previous step. We calculated it in the previous step when we converted the dN into the top of the atmosphere spectral radiance. D, there is also D in this equation. D, this is nothing but the Earth-Sun distance. in astronomical units, AU. E sun lambda is the mean solar extra exoatmospheric irradiance, and theta s is the solar zenith angle, and theta s solar zenith angle is 90 degree minus the sun elevation. Anyway, so these final three quantities d, e sun lambda, and theta s, they are given in a Landsat handbook. If you are using Landsat, given in Landsat handbook. Landsat, I'm taking the example of Landsat because Landsat is first of all freely available, and secondly, it is probably one of the. The temporal coverage of Landsat is probably one of the largest one. So this is it. Any doubt from this part, because this is something which forms the crux of remote sensing based exercises. Any doubt from this part?
सर इतना डीपली हमने पढ़ा नहीं है सर.
ओके ओके ओके. अभी अभी क्लियर लग रहा है क्या?
सर आप जो बता रहे हैं वो मतलब कि ठीक तो लग रहा है कि मतलब जो सर ने पढ़ाया उसके एग्जांपल्स आप बता रहे हैं.
हाँ
और इनको अगर दोबारा से रिवाइज करेंगे तो शायद अच्छे समझ में आ जाएंगे.
हाँ, ऐसा टेंशन का कोई नहीं है. सो एग्जाम में प्रोबेबली क्वेश्चन ऐसा आएगा कि यू बी प्रोवाइडेड विद द DN straight away. Okay, and then they would ask you to, they would give you these values, L max, L min, and everything. You just have to put the value and get the answer. ऐसा ही एग्जाम में क्वेश्चन आने वाला है. It's not going to be very tough. But in order to explain that, I thought of starting it from the very basics. Okay, so all these values will be provided to you. These numbers, they will be provided to you. You don't need to memorize them. Okay, so let's move to the next list of questions. So we have transitioned from the questions based on the conversion of digital number to spectral radiance to now on the storage requirement of the sensor. A digital image consists of 1200 by 1200 pixels. If it is an 8-bit image, what is the memory required to store this image? Okay. So let me give a common formula for this. Memory requirement is the number of bands in the image times the number of lines in the bands.
बट सर मेमोरी से रिलेटेड क्वेश्चन थ्योरी कुछ सर ने बताया नहीं शायद अभी तक.
This is actually, very basic actually, and in some other remote sensing books, this is already provided. I am following Lil Sand and Kiefer. Sir is also following the same book, by the way. Lil Sand and Kiefer. It's one of the most basic textbooks on remote sensing, by the way. So, I'm just taking up an example just to understand how the memory changes, and it's nothing difficult, by the way. It's all based on logic.
यस सर.
Okay. Times the number of pixels per the line times the number of bits. Per pixels. So how does it come to be? Let's say there is a 3-band image. Okay. So this is band number 1. Just taking an example. This is say band number 2, and so on and so forth. Okay. So there are lines 1, 2, and 3. Okay. So per line there are 4 pixels in each of the band. So total number of and let us say this is an 8-bit resolution image. So number of bits per each pixel means the total number of discretizations would be the bits would be 8-bit. You just multiplying it by the number of lines pixels per line. Sorry. So per line there would be 4 pixels. Multiply it by the number of lines per band. So there are, let us say, 3 lines. Multiply it by the number of bands. So let us suppose there are till band number 5 for it. So this is how you will get the total memory in bits. Okay, but let's solve this question first. We would take another slide to do that. So it is basically a 1200 by 1200 pixel image. The number of bands is not stated, so let's take the number of bands as 1. And it is an 8-bit image. So what is the memory required to store it? So let's use that formula. 1 band times the number of lines is 1200 times the number of pixels per line is 1200 times the number of bits per pixel, which is 8 in this case. So this comes out to be 11.52 into 10 to the power 6 bits. But usually we need to report this in units of megabytes or kilobytes. So let's see how this unit conversion happens. So one byte represented as B is basically equal to 8 bits represented by small b. Sorry. (1000) bytes would be equal to 1 kilobytes. Represented as KB, capital B. 1000 kilobytes KB equal to 1 megabyte MB. There is also another sort of conversion in computer science.
It is 1024.
Yes, that is what I'm writing now. Exactly. So 1024 bytes B is something known as 1 kibibytes. It is written as this. And some people also write kibibytes as kilobytes, and that is how this confusion erupts. So you are saying the same thing, right?
Yes, sir.
Yes. So and 1024 kibibytes KIB is 1 megabytes. 1 megabyte. Sorry, maybe byte. Okay. So this is represented as MIB. But for the sake of this course, for the sake of this question, let's just focus on megabyte, MB, and not maybe byte. Okay. So the answer which we got was in bits. Let's convert that number of bits to number of megabytes. Megabytes. Okay. So let me take another slide to show that. So answer was 11.52 into 10 power 6 bits. Let's convert it. So 11.52 into 10 power 6 bits divided by 8 to convert it into bytes, and divided by 10 to the power 6 to convert it into megabytes. So we would get 1.44 megabytes. Let's solve another such question, but this question would have different bands also. So a satellite image has 7 bands, each of 9000 by 9000 pixels, and 8-bit radiometric resolution. What is A? What is the total memory needed to store this image in megabytes? And B, if this satellite can transmit the image at 10 megabytes per second, how long will it take to transmit the image to the ground? So the first question is straightforward. The memory requirement is number of bands times number of lines times number of pixels in each line times number of bits per each pixel. Straightforward. It's very straightforward. We just put the values in the equation. So uh, it would be 7 number of bands, 9000 lines, and per line there are 9000 pixels, and 8-bit is the radiometric resolution. So this would be in bits. Let's convert it directly into megabytes. So 7 into 9000 into 9000 by divided by 8 to convert bytes into bits into bytes, and divided by 10 to the power 6 again to get in megabytes. So this comes out to be 567 megabyte. Question number B is if the satellite can transmit the image at 10 megabytes per second, how long will it take to transmit the image to the ground? So how to do it? Any idea about it? It's very straightforward again. Any idea, Saket? Saket also.
Yes, sir.
Yeah. So how to do this part? The part B. Yeah, Saket. Any input from you on part number B? So we are given the rate. Rate is 10 Mbps, means 10 megabyte per second, and we also know the total storage, which is 567 megabytes MB. So to come to the time,
सर सैटेलाइट से सर जितनी इसकी डिस्टेंस होगी ग्राउंड की,
डिस्टेंस को तुम छोड़ ही दो, क्योंकि आई मीन मेगाबाइट पता चल गया है, और एमबीपीएस जो आया है वो डिस्टेंस की कैलकुलेशन से ही आया है साकेत, ठीक है? तो
यस सर,
तुम बस यूनिट देखो यहाँ पे, द वन ऑफ द यूनिट्स इज मेगाबाइट पर सेकेंड एमबीपीएस, और एक यूनिट है मेगाबाइट, स्टोरेज है मेगाबाइट. सो हाउ डू वी कम टू टाइम? जस्ट डिवाइड, राइट? एमबी को
Yes, sir.
एमबी पर सेकेंड से डिवाइड करोगे तो सेकेंड्स आ जाएगा, राइट?
यस सर.
That's it. That's it. This is very straightforward. So the time would be equal to. Oh, sorry. Let me full screen it. 567 megabytes by 10 MB per second. So it comes out to be 56.7 seconds, nearly equal to 1 minute. So in around 1 minute, you can transmit this large amount of data at a speed of 10 Mbps to the ground from the satellite. Let's take another example of, similar field, but this example is about hyperspectral remote sensing features. So panchromatic is the one in which there is only one band. Multispectral is the one in which there are multiple bands, maybe around 10 to even 50. But those bands may not be contiguous in nature. They may not be continuous in nature. And hyperspectral are the ones in which there are more than 100 bands in general. and they have to be continuous also. So that is how we compare between the three different domains of remote sensing: panchromatic single band, panchromatic single band, multispectral, multiple bands, maybe till maybe from 5 to, let us say, even 50 or even 100. I mean, this number arbitrarily varies, but these bands need not be contiguous, contiguous or continuous. Both are similar. Contiguous means there is no gap in between the wavelengths. So they may, I mean, these bands may be the ones in which there may be gaps. And then finally there is hyperspectral, very large number of bands, usually greater than 100, maybe even 224, as in the case of average sensor, which I mean, the example of which we are taking. And the bands should always be contiguous. That is the basic difference between a hyperspectral remote sensing feature versus a multispectral remote sensing feature. Let's go back into the Landsat 8 bands. We took up an example, in question number 5. So Landsat 8 is basically a multispectral remote sensing feature, right? And you can see that there are some discontinuities in between. So in band 6, the wavelength was 1.57 to 1.65. In band 5, it ends at 0.88. So from 0.88 to to 1.57 microns, there is a gap. Then again between 6 and 7, between 1.65 and 2.11, there is a gap. Same is the case with band 10 and the bands previous to that. There are gaps in those cases also. And why are these gaps present? Why can't we find the spectral radiance or the DNs or the reflectance for each wavelength range? Why is it so? Uh, uh, any idea? Any comments you would like to make on this question?
No, sir.
Okay, so there are gaps because there are something known as atmospheric windows. So the radiation can pass through only for a particular range of wavelengths, and for some other range of wavelengths, most of the radiation which comes to the surface of the Earth from the sun actually gets either absorbed by the atmospheric constituents like the molecular gases or dust or clouds, or they get scattered so much that the reflection that the reflectance, I mean the reflected radiance, which is actually finally sensed by the satellite sensor, that is almost null and void. So that is why the remote sensing works only for a particular wavelength ranges. Now let's move to that question of hyperspectral remote sensing. The question states that uh, the average sensor can take an image in 224 bands. Okay. At 8-bit radiometric resolution. A. If each image has 2000 by 2000 pixels, what is the memory required for this image in megabytes? And B. If the image can be transmitted at 10 Mbps, what is the time taken to transmit this image to the ground? So we are solving the same questions, but for this question we have taken a hyperspectral sensor. The previous one was a multispectral sensor. So hyperspectral means the number of bands are huge, and they need to be continuous. So let's solve it again. So I just wanted to give a brief about what AVERIS is. AVERIS stands for Airborne Visible Infrared Imaging Spectrometer. So it's a hyperspectral remote sensing sensor. It has 224 contiguous spectral bands, spectral bands, and wavelength ranges from 380 to 2510 nanometers. So that is a brief about AVERIS. Another famous hyperspectral sensor is Hyperion. Anyways, this question is about AVERIS, so let's solve this question. So we are using the same formula, number of bands times number of lines per band times number of pixel per line times number of bits per pixel. So just plug in the values: 224 bands, 2000 lines, and each line has 2000 pixels times 8 bits. Let's convert it into megabytes. So 224 into 2000 times 8 bits. By converting bit to byte, will need you to divide it by 8 and then divide it by 10 to the power 6 more to convert it into megabytes. It comes out to be 896 megabytes finally. And this was question number A. And question number B was the time required at 10 Mbps. So time,
सर
yes.
सर इसके सर जो पहले वाला क्वेश्चन था उसमें ऊपर बिट्स का मल्टीप्लाई नहीं किया गया था।
कौन से ऊपर में तुम बोल रहे हो?
न्यूमिनेटर में।
Oh, sorry. Yeah,
यस सर।
yeah. Very sorry for that. Yeah. I mean, when I moved from step number 1 to step number 2, I forgot to add this 8, but the answer is correct anyways. I have solved it keeping that in mind.
सर
Thanks for informing. So time is again the number of megabytes by the number of uh, rate, the rate. So this would be 896 megabytes by 10 MB per second. This comes out to be 89.6 second, nearly equal to 1.5 minutes, 1 minute and 30 seconds. So the time changes. The earlier time was 1 minute. It was only a 7 band satellite image. This one is a 224 band one. So of course, I mean, as you increase the band and as all the other factors remain constant, the time would also increase if the rate is same. Let's take one final question from this series of memory requirement based questions. A proposed replacement of the existing average sensor would require a 14-bit image in 224 bands. So average works on 8-bit, but this proposed sensor, let us suppose a hypothetical one, would acquire a 14-bit image in 224 bands. A, if the image is 2000 by 2000 pixels, what is the memory required for this image in megabytes? And B, if the image can be transmitted at 10 Mbps, what is the time required to transmit this image to the ground? So let's solve it. Same question, but in place of 8-bit, we have to put 14-bit. That's it. So again, number of bands times number of lines times number of pixels per lines times number of bits. That's the formula. It's very straightforward. So it would be 224 bands for average. I mean the replacement of the existing average sensor times 2000 times 2000 times 14. This is in bits, divided by 8 to convert bits into bytes, again divided by 10 power 6 to convert bytes to megabytes. So we get it as 1568 megabytes. So just compare when we move from 8 bit to 14 bit, the number of the storage of course increases. And what would be the time? Time would be 1568 megabytes per 10 MB per second. So this would come out to be 156.8 second, which is nearly equal to 2.5 minute. So as you increase the as you moved into a finer radiometric resolution from an 8-bit one to a 14-bit one, the time increased by almost 1 minute. It was 1.5 minute for an 8-bit formulation. Now it is 2.5 minutes, almost 2.5 minutes. Now another different set of questions. In overall, we would be solving 11 different questions today. Now coming to another set of questions. So this set of questions, would deal with the conversion of DN from one radiometric resolution to another radiometric resolution system. So let's solve it. So the question states that a remote sensing system with a radiometric resolution of 6 bits assigns a DN of 24 to one surface and 40 to another. What would be the equivalent DNs for the same surfaces if the measurements were taken with a 3-bit sensor? So what would be the DN range? DN range by a 3-bit sensor. This would range from 0 to 2 to the power 3 minus 1, that is 0 to 8 minus 1, that is 0 to 7. So it's very straightforward. In general, if there is a n-bit sensor, then this implies range would be from 0 to 2 to the power n minus 1. So for an 8-bit system, the range would be from 0 to 255 and so on and so forth. So for a 3-bit sensor, let us just write the DNs. DNs have also should always be in integers. They are never fractional terms. Okay, so it can range from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. What would be the DN value for a 6-bit sensor? So for 0, sorry, what is this? For 0, the lowermost DN value for any bit, any radiometric resolution is always 0. So the highest value for a 6-bit sensor is 2 to the power 6 minus 1, which is equal to 64 minus 1, which is 63. So you put it here, it would be 63. Now you have to fill the gaps. You have to fill what these values would be. One way to do it is that just take a ratio. 63 divided by 7 is basically 9. Just multiply it by 9 for each of the cases. 6 times 9 is 54. 5 times 9 is actually 45. 4 times 9 is 36. 1 times 9 is 9. 2 times 9 is 18. 3 times 9 is 27. So now you get all the DNs basically, and this question asks you to find out the equivalent DNs in a 3-bit sensor. Okay, so DN equal to 24 and DN equal to 40. You need to convert from a 6-bit resolution to a 3-bit resolution. So DN equal to 24 in 6-bit will change DN equal to 24. So it is between 18 and 27. And we always need to put DN values in an integer format. So In 3-bit, in between 80 and 27, let's take it is 24. 24 is closer to 27. So for a 3-bit system, let's 27 for which the equivalent DN value at a 3-bit resolution is 3. So let's take the DN as 3 itself in a 3-bit system. The next question is DN equal to 40 in a 6-bit system. We need to find out the corresponding 3-bit DN. So the DN would be 40. 40 is between 36 and 45. Okay. 40 is closer
36
to.
means that.
Yes, yes. Please ask.
So 36.
Yeah, but we need to find out DN corresponding to 24 and 40, right? So corresponding to 40, what would be the DN in a 3-bit resolution? Yes, yes. Tell me. Please feel free to. Yes, Saket, please feel free to answer.
Sir, I think it is 36.
Exactly, exactly. It would be corresponding to 36, which is DN equal to 4 for a 3-bit resolution. Correct. So this is how we solve the conversions. Let's take another example for this same series of question. The pixel values containing the DNs of a 5 by 5 image are shown below in an 8-bit resolution. Convert the image DNs to a 5-bit resolution, and B, a 3-bit resolution. So I have not given the 5 by 5 image DNs here. I am giving it now. The DNs are 123, 162, 200, 147, 93, 137, 157, 165, 232, 189, 151, 155, 152, 141, 130, 205, 101, 100, 193, 115, 250, 50, 75, 88, 100. So this is that 5 by 5 image in 8-bit resolution. So this is that image. I mean, you will only get numbers basically. Okay, so we have to convert this 8-bit image, the 5 by 5 8-bit image, into a 5 by 5 5-bit image and a 3-bit image, 5 by 5 3-bit image. So let's understand how this actually happens. The basic step is that dividing the image by 2 will reduce its gray level, which is nothing but the resolution by 1 bit. Why by 2? Because this is 2 to power n kind of a quantization. I expressed it in I expressed it here. It's a 2 to power n kind of quantization. So whenever you divide it by 2, the quantization, I mean the radiometry resolution will decrease by 1 bit. Okay. So the first question is on converting the 8-bit image to a 5-bit image. Let's see how we do that. The first question is about the conversion. Convert 8-bit to 5-bit. We also got to know that when we divide it by 2, 1 bit gets reduced. So 8-bit to 5-bit, 3 bits will be reduced. 8-bit minus 5-bit is 3 bits. Okay, so just divided by 2 to the power 3, which is equal to 8. This implies we divide the image DNs by 2 to the power 3, which is equal to 8, to get a 5-bit image. Okay, so you just divide each element of this image by 8, and then round them up, because the DNs are never fractional numbers; they are always integers. Just round them up, and you get the DNs corresponding to 5-bit resolution. So the final answer would be, I'm straight away writing the final answer: 15, 20, 25, 18, 11, 17, 19, 20, 29, 23, 18, 19, 19, 17, 16, 25, 12, 12, 24, 14, 31, 6, 9, 10, 12. So this would be the new image DNs at a 5-bit resolution. Now we are solving another question, which is changing from an 8-bit image to a 3-bit image. So let's do that. To obtain 3-bit image, what do we need to do? So 8-bit minus 3-bit is 5-bit. So we need to divide by 2 to the power 5, basically. Image divide 8-bit image DNs by 2 to the power 5, which is equal to 32. To finally get, I'm finally straight away writing the answer. You need to round it up also. I mean, divide the elements, the 8-bit elements which are given in the question, by 32, and then you need to round it up, because DNs are never non-integer values. So the 3-bit values would be 3, 5, 6, 4, 2, 4, 4, 5, 7, 5, 4, 4, 4, 4, 4, 6, 3, 3, 6, 3, 7, 1, 2, 2, 3. So this is the 5 by 5 image, which is in 3-bit radiometric resolution. So it's as simple as that. Before ending the class, I would like to discuss a few two more concepts. The first concept is the signal to noise ratio, and I would like to relate it with this example of Landsat 8 bands again, using signal to noise ratio. And the final one would be about zooming of the images, zooming on or shrinking of the images, which you use frequently, but many people don't know the science behind it or the mathematics behind it. So these would be the final two discussions for today's weekly live session. So let's see, the signal to noise ratio, or in general written as SNR. The name itself states that it is the ratio between signal to noise. So data recorded on the sensor, it has some signal. Let us say that is the reflectance or the radiance, and it also has some noise. Noise maybe because of aberrations in electronics, moving parts or defects in scanning systems. These defects may happen when the scanning systems get older, so they are inherently there. So we would ideally want to have a large value of signal to noise ratio. A larger SNR would depict that the noise is low and the signal received by the sensor is large. That is what we would want to have ideally. But there are some issues also. Increasing the spectral, spatial, and radiometric resolution of of a system may decrease the SNR to such an extent that the data may not be reliable. SNR also depends on the strength of signal available. So, to maintain a uniform SNR, the bandwidths are adjusted for different bands. Uniform SNR to be maintained. The bandwidths, I mean, for each of the bands are designed in such a way that more or less the signal to noise ratio is more or less uniform across the bands, and that is why the bandwidths vary, and that is what we see in the Landsat 8 band formulation also. So as you see that the bandwidth was 0.02 microns in band 1, it has suddenly shot up to 0.06 microns in band 2, then 0.06 in band 3, in band 4 it is 0.03 microns, in band 5 it has again shot down to 0.03 microns. So I mean, so these bandwidths are in general designed keeping in mind both the uniformity of signal to noise ratio as well as the presence of atmospheric bands. And in general there is a massive trade off between uh, the spatial resolution and the spectral resolution. So in order to obtain, I mean, as we move into the higher wavelengths, the wavelengths are increasing in general. Wavelengths increase as we go down in the table. So the frequencies decrease. So the energies also decrease. So as we are moving into higher wavelength ranges, longer wavelength ranges, the energies decline. So we need to have a greater amount of area to detect a considerable amount of energy, and that is why you can see that the spatial resolution has changed from 30 to 100 meters as we move into higher wavelength ranges. So that's one of the reasons behind it. So we are done with this part also. The last part of today's discussion would be on the zooming and the shrinkage of the images. Let's see how they're done. How do we zooming and shrinking digital images? How do we zoom them or how do we shrink them? It is something which I thought of discussing just out of curiosity, from because from the next weekly live session I would be taking up some coding examples. So we would be needing to interpolate some of the results. That is what would be required from us from the next weekly live session onwards. And you may be asking me how these interpolation techniques uh, started. I mean, what's the basic mathematics behind those interpolation techniques? So, just to have a background of that, I plan to discuss this in today's weekly live session itself. So, zooming, the part one is zooming, which is basically scaling of an image of an image area, let us say A, of let us say W by H pixels width by height by a factor, let us say the factor is S, while maintaining the spatial resolution. We are not changing the spatial resolution. This implies output has SW times SH pixels. So there are some basic steps of zooming. The first one is creation of new pixel locations. And the second step is assignment of gray labels to those new locations. So in case you're not understanding it, we will be taking up a couple of examples and it would be crystal clear after that. So methods of grayscale assignments. There are several methods of grayscale assignments, by the way. Grayscale assignments. But I would discuss the two most commonly used grayscale assignment methods and which are the simplest ones also. The first one is basically the nearest neighbor interpolation. It is the simplest one. It requires the least amount of time. In general, for satellite-based images, you will not find just a 5 by 5 pixel image. By the way, the satellite images are huge. The images may be around 2000 by 2000 pixels or something of that magnitude. They are massive. Okay, so for them, saving up the time or the computational time is also very important. So the simplest one is the nearest neighbor interpolation technique. Nearest neighbor interpolation technique, it is also known as the zero order hold. Okay, let's try zooming an image, zooming by 2x. 2x means twice the original width to height. So let us suppose the original image is this 69, 50. These are the DNs, by the way. 45, 60, 66, 30, 55, 80. So this is the original image. The next stage is to expand the rows. Rows expanded in nearest neighbor algorithm. So 69, 45, 30. The first row, the first column will stay as the first column. We will then duplicate it. 45, 30. Okay. Then the next column of the original image was 50, 60, 55. We will duplicate it again. 50, 60, 55. 50, 60, 55. The third column of the original image, we will duplicate it again. 80, 66, 80, 80, 66, 80. Now expand. Sorry, this was the columns expanded. Now expand rows. What do we do in that case? It's very straightforward. We will duplicate it along the rows this time. Okay. So the first row originally was 69, 69, 50, 50, 80, 80. We will just duplicate this row. 69, 69, 50, 50, 80, 80. Now the second row was 45, 45, 60, 60, 66, 66. We again duplicate it. 45, 45, 60, sorry. Yeah, now it's connected. Sixty, 60, 66, 66. Again 45, 45, 60, 60, 66, 66. And the final ones again written twice, duplicated. 30, 30, 30, 30, 55, 55, 55, 55, 80, 80, 80, 80. So this is the image with rows and columns expanded. Now let's look at the second basic method of grayscale assignment, which is the bilinear interpolation or a first order hold. Any doubt from this, by the way? Anything to ask from this? It's very straightforward, right?
No, sir.
Yeah. Okay. Let's move to the second method of filling up the grayscales. That is bilinear interpolation. Which is also called as first order hold because it's linear in nature. That is why it's first order. So the original image, we are again taking the same original image, 69, 50, 80, 45, 60, 66, 30, 55, 80. So this was the original image. Let's expand the columns. The first stage is very simple. 69, 45, 30. The first column will stay as first column. Okay. The second column of the original image will become the third column in that case. 50, 60, 55. And the third column of the original image will become the last column. So it would be 80, 66, 80. And how do you fill up the gaps? There are gaps in between. The gaps are filled up by linear interpolation between them or arithmetic average. So this would be 59, this would be 52, this would be 42, this would be 65, this would be 63, this would be 67. Now image with rows and columns both expanded. It's again very straightforward. Retain the first row of this expanded one, like this: 69, 59, 50, 65, 80. We have retained it. The second row will become uh, the in between row. So that would be 45, 52, 60, 63, 66. And the last row will become the last row again, final row again of this expanded image: 30, 42, 55, 67, 80. Now how do we fill up the gaps? These gaps, just the way we did it earlier. We fill them up by taking an arithmetic average or linear interpolation between the two. So 45 and 69, the one would be 57. 45 and 30 would be 37. 59 and 52 would be 55. 52 and 42 would be 47. 60 and 55 would be 55. 60 and 55 would be 57. We cannot take decimal values, so we are retaining the integers. 65, 63 would be 64. 80, 66 would be 73. 63, 67 would be 65. 63, 80 would be 73. So that is how we get into a 2x resolution, by the way. This is the final zoomed image by bilinear interpolation technique. Now, one thing you will observe is that the original image was 3 by 3 or m by n. The final images in both the cases are actually 1, 2, 3, 4, 5, 6. Okay, they are in general of the type 2m by 1 times 2n minus 1, 2m minus 1 times 2n minus 1. So, in order to retain that 2x zooming, you just need to add an additional row. That additional row can be added up by some techniques known as padding. You can just either repeat this row in the very end or do some other higher order mathematical formulations. But this is how we actually come into a 2x zooming approach. Finally, we would discuss, we would take up one example of shrinkage. We already discussed about zooming, so let's take up an example of shrinkage also, shrinking of the images. How do we shrink images? So B is shrinking. So what do we do here is that it is something also known as a row column deletion. We are doing the exact opposite thing. I mean, with respect to zooming in shrinking. So let's take up an example of shrinking by 1/2. Let us suppose the image was 69, 69, 50, 50, 80, 80. Again, repeating it again. We are taking just the example of the nearest neighbor algorithm. 80, 80, 45, 45, 60, 60, 66, 45, 60, 60, 66, 66. 55, 55, 80, 80, 80, 80. So this, let us suppose this is the original image. Now delete rows first. So we would get to, yeah, delete each row in between. So 69, 69, 50, 50, 80, 80, then 45, 45, 60, 60, 66, 66, and finally 30, 30, 55, 55, 80, 80. Now delete columns. The final image after shrinking would come out to be 69, 50, 80, 45, 60, 66, 30, 55, 80. So this is the final shrinkage image, the final shrunk image. This is the one. Okay, so this is it for the class, but I will uh, just discuss what we discussed today uh, in brief. The first question which we discussed today were about the different color values in a three color, three band Landsat 7 image. It's basically a question of permutation combination itself. I mean, if you are checking it in that sense. We found out that when we move from a Landsat 7 image versus that of a Landsat 8 image, I mean, of course, the radiometric resolution increased by 4 bits from 8 bit to 12 bit. The number of color values would increase massively. For Landsat 7 image, for a 3 band formulation, the number of color values would be in excess of 16 millions, whereas the same thing for Landsat 8 would be in excess of 68,719 million. So it's a massive increase as we change the
Sir,
radiometric resolution.
sir, what is the basic difference between Landsat 8 and 7?
The basic difference is that the radiometric resolution has changed. In Landsat 7, the radiometric resolution is 8 bit. This is the radiometric resolution. Radiometric resolution. So the number of discretizations in Landsat 7 would be 2 to the power 8, whereas the Landsat
Yes,
8,
sir.
yes, sorry,
Yes, sir. Continue.
okay, and the number of discretizations in Landsat 8 would be 2 to the power 12. So that's the only
Hmm.
thing. I mean, if you observe an image, the clarity would be more in Landsat 8.
अब सर मान लीजिए कहीं पर लिखा Landsat 9 भी होता है.
अभी Landsat 9, Landsat नेक्स्ट भी आ गया है एक्चुअली. आई थिंक आ गया है कि नहीं आ गया है, मैं थोड़ा चेक करता हूँ. मैं Landsat बहुत दिनों से यूज नहीं कर रहा हूँ. सो अभी आ गया है क्या? लेट मी चेक. Landsat नेक्स्ट करके कुछ है, मतलब समथिंग लाइक दैट. Launch date. Let's check it out. Plan to launch in late 2030. So it would take some time. And Landsat 9 has been launched already, launched on September 27, 2021. So probably you can find its data already on USGS Earth Explorer. You know that, right? How to use USGS Earth Explorer?
Sir, I want to ask that अगर Landsat 9 आया तो उस जैसे कि Landsat 7 में 8 बिट आ रहा है, Landsat 8 में 12 बिट आ रहा है, तो उसमें बिट बढ़ेंगे.
शायद मैंने चेक नहीं किया. Let's check Landsat 9 resolution. The spatial resolution is same. Let's check the radiometric resolution. Can you see my screen, by the way?
Yes, sir.
Okay, Landsat 9 can differentiate 16,384 shades, Landsat 8 at 12 bit, it can differentiate 4096 shades. So let's see. 16,384 shades मतलब कितना बिट हुआ फिर? 2 to the power n is ये, ठीक है? So 16 2 times
14,
कितना 14 आ रहा है क्या?
शायद 16 होना चाहिए।
अगर 16 है तो मेरा देखता हूँ 2 to the power 16, मेरे पास कंप्यूटर कैलकुलेटर है। 2 to the power 16 is 65,536। नहीं, उससे कम है। 2 to the power 14 है शायद, या तो
14
14
है,
बिट्स
ओके।
सर, 14 बिट्स सर। ओके, 16,384 शेड्स मतलब इक्वल टू 2 to the power 14, मतलब 14 बिट्स में काम करेगा। या दे आर इंक्रीजिंग द, दे हैव इंक्रीज द रेडियोमेट्रिक रेजोल्यूशन। यू आर करेक्ट। Then we discussed the next question, which was discussed about, was about the data storage. We learned how to store data in band BIL format, that is the band interleaved by pixel line. Then in the BIP format, which is the band interleaved by pixel, and finally in the band sequential format. We learned that in BIL, we are filling up each line of each band first. I mean, the first line of band 1, then the first line of band 2, then the first line of band 3, then the second line of band 1, second line of band 2, second line of band 3, third line of band 1, third line of band 2, and third line of band 3. That is how we move in BIL. In BIP, we store the pixel values first. The first pixel of band 1, then the first pixel of band 2, then the first pixel of band 3, then the second pixel of band 1, second pixel of band 2, second pixel of band 3, till we move into the ninth pixel position of band 1, ninth pixel position of band 2, ninth pixel position of band 3. And in band sequential, we fill up the first band first entirely, then we fill up the second band first, entirely, and then the third band entirely. That is how we store data in band sequential BSQ format. Then we took up an
तो
example.
सर
Yes, sorry.
क्वेश्चन था सर, इसमें सर फोर्थ क्वेश्चन जैसे है, थर्ड है, सेकंड है, इनमें सर जो एग्जाम में क्वेश्चन आएगा तो क्या फिलअप करने के लिए आएगा?
ये आ सकता है, ये मेरे समय में आया था। मैंने रिमोट सेंसिंग अपने मास्टर्स में जब लिया था, कोर्स 11 क्वेश्चन मेरे फाइनल एग्जाम में आया था। बट इट्स वेरी सिंपल राइट, नाम से ही पता चल जा रहा है। बीआईपी है मतलब पिक्सल है, तो पिक्सल को तुम पहले भरो, पिक्सल वाइज भरो। बीआईएल है मतलब लाइन वाइज तुम पहले भरो। अब इजी है ना, मतलब ऐसा कुछ, मतलब याद करने का कुछ नहीं है इसमें, राइट?
नहीं सर, वो इजी तो है, लेकिन बस पूछ रहे थे कि मतलब ये जो एग्जाम हो गया एनपीटीएल का, तो इसमें भी ये क्वेश्चन आ सकता है
आ
इस टाइप
सकता
का?
है। मतलब मैंने मास्टर्स में ये वाला जब कोर्स लिया था अपने एमटेक में, तब ये वाला क्वेश्चन मेरे फाइनल एग्जाम में आया था, मुझे अच्छे से पता है। मैंने वो वाला कोर्स आईआईटी गुवाहाटी में लिया था, मैंने मास्टर्स आईआईटी गुवाहाटी में किया है, तो मतलब उस बार की कहानी बता रहा हूँ। तो आया था ये वाला क्वेश्चन आया था, इसलिए मैंने सोचा डिस्कस कर लूँ ये क्वेश्चन। Then the fifth question which we discussed was about the conversion of DN into the top of the atmosphere spectral radiance. We did it using this gain and the bias concept. So this gain and the bias would depend on the bands also. These are already available in the metadata of the USGS Earth Explorer. So we can look at it and convert the DN into the top of the atmosphere spectral radiance. It's as simple as that. So this was the first method. The second method was to use Lmin and Lmax. So through that also you can find out the top of the atmosphere spectral radiance. So we took up another example. The next example was this, where we converted a certain DN value of, let us say it's 400 DN to its spectral radiance. The second step would be to convert this radiance which we arrived at from by converting DN into radiance to the top of the atmosphere reflectance. So this is the expression which would through which we can get the top of the atmosphere reflectance. Reflectance, as we all know, is the ratio of the radiance to the irradiance, and it will always vary between 0 and 1. So it depends on the Earth to Sun distance, the atmospheric irradiance, and the solar zenith angle. These values are already given in the Landsat handbook. Then we took up a few examples based on the memory requirement or for storage for different sensors and for different satellites. We understood that as we move into finer radiometric resolutions, the memory requirement increases, and as we move into the greater number of band numbers, the memory requirement again increases. Finally, we took up a couple of questions related to conversion of DNs from a given radiometric resolution to a different radiometric resolution. So the first one was converting from a 6-bit resolution to a 3-bit resolution, and then we took up a very similar kind of question in which we converted an 8-bit resolution 5 by 5 image into a 5-bit resolution and a 3-bit resolution. We understood that as we change the bits, we need to either divide it. I mean, if we are basically coarsening the resolution, or we need to multiply it by a factor of 2. If we are basically going into finer resolutions, radiometric resolution. So that is the funda behind these questions. We also understood what this signal to noise ratio and noise ratio is, and how the bandwidths are decided based on the signal to noise ratio. And finally, we took up a couple of examples to show the zooming and the shrinkage of images. The grayscale assignments can be done using several methods, but we discussed about the nearest neighbor interpolation, in which we are just repeating the values from the nearest neighbor, and using the binary interpolation, in which we are basically filling up the gaps by a linear interpolation. And we also took up an example of the shrinking of the image. So that's what we discussed today. If there is any question, please feel free to ask from me. Anything to ask?
सर लास्ट क्वेश्चन में सर मतलब पहले कॉलम फिल करना है, इसके बाद में रो फिल करना है, ऐसे ही ना?
तुम अदर वे राउंड भी जा सकते हो, कोई इसमें गड़बड़ नहीं है. तुम पहले रो को भी फिल कर सकते हो, बाद में कॉलम को भी कर सकते हो. आंसर वुड बी सेम इन बोथ द केसेस, राइट?
यस सर.
You can do whatever you want, मतलब, but answers are same. Basic mathematics है ये तो कोई ये दिक्कत नहीं. Anything else?
सिमेट्रिक है सर.
Anything else you want to discuss or ask? कोई और क्वेश्चन है क्या साकेत?
क्वेश्चन था.
हाँ बोलो, फिर बोलो, पूछो.
सर जिसमें आप सर 12,000 पिक्सल इंटू 12,000 पिक्सल था क्वेश्चन में.
ओके, which one? 12,000 or 2,000?
12,000 था एक क्वेश्चन में.
This is 9,000 by 9,000. This is 2,000 by 2,000.
वाला.
This is 2,000 by 2,000.
1200 सॉरी.
होगा. ओके, कोई होगा क्वेश्चन. मुझे दिख तो नहीं रहा है ऐसा कोई क्वेश्चन.
सर 1200 है वो.
कौन सा वाला? अच्छा होगा. तुम क्वेश्चन क्या पूछ रहे हो ये बोलो मुझे. What is your question exactly?
सर उसमें ये पूछना था सर, जो उसमें ऐसा बैंड लिया हुआ था तो 3x4 का बैंड लिया हुआ था.
I didn't get you. Which question are you talking about? I mean, let me show you each question. Okay.
Yes sir.
The first question was this. This has nothing to do with 1200. This is the second question. Second, third, and fourth questions are on the data storage. Nothing to do with 1200 again. This is the next question. Again, nothing to do with 1200. Then question number 6. Yeah, 1200. Okay. So this one, right?
Yes sir.
Yeah. So it is only a single band image. They have not given you the number of bands. So let's assume that the number of band is 1. So this term would be 1.
सर जो सर नीचे सर ये बैंड्स बने हुए हैं नीचे B1 और B2, इसमें सर
सर क्या बोल रहे हो? आवाज कट गई तुम्हारी.
1 और B2, बैंड 1 बैंड 2 सर ये 3/4 के हैं.
हाँ, ये मैं बस एक्सप्लेनेशन के लिए समझा रहा था ये चीज. ये बस एक्सप्लेनेशन के लिए था एक्चुअली. ये इस क्वेश्चन से रिलेटेड नहीं है. ये इलस्ट्रेशन है ना, नथिंग टू डू विद दैट. मैं ऐसे समझा रहा था कि कैसे होता है. क्योंकि 12,000 by 12,000 इतना बड़ा इमेज बनाना तो पॉसिबल नहीं है, तो मैं 3/4 करके समझा रहा था. समझे? 3 लाइंस होंगे. देयर वुड बी 3 लाइंस. देयर वुड बी 4 पिक्सेल्स पर लाइन. And if it's an 8-bit resolution image, then it multiply with 8, and if there are 5 bands, then multiply with 5. मैं समझाने के लिए कर रहा था. It was just for the sake of illustration. It has nothing to do with this question number 6. Okay. I hope it's clear.
Yes, sir.
Okay. Anything else? Anything from today's illustration?
Nothing.
Nothing. So I think I shall stop recording now.